everyone. In this video, we will introduce hypothesis tests, talk a little bit about the general outline of them and how they are used. So let's get started. We'll begin by going through the outline of a hypothesis test and just talking about the four major steps to doing any hypothesis test. We'll spend some time exploring how to write statistical hypotheses and figure out how to word a research question in terms of a formal test. We'll talk about how to make a conclusion on something called a p-value, and then we'll talk a little bit about types of error in this video as well. So a hypothesis test is a procedure for evaluating the evidence for or against a specific research claim based on some probability called a p-value. So we'll set up two competing research hypotheses. Based on the data, we'll assess some evidence for or against them. So there are four basic steps to any hypothesis test. The first step should always be to write out the null and alternative hypothesis, figure out what the research claims actually are. Second step is to collect evidence from our sample and calculate what's called a test statistic. Third step is to translate that test statistic into a probability called a p-value. And then finally, we will make a decision based on that p-value. Before we go much further in this video, I do want to remind you that at the beginning, we're focusing on the concepts here. So we'll talk a lot about steps 1 and a lot about step 4 because those are consistent from hypothesis test to hypothesis test. Throughout the rest of the course, we'll see lots of little tweaks on steps 2 and 3, depending on what our data actually looks like. So let's talk about step 1. Step 1 is to write the competing hypotheses, and we've got two hypotheses that we want to evaluate. The first one is called the null hypothesis. This null hypothesis is some statement or some assumption about the exact value of a population parameter. So we will assume that our population value is equal to something. That something should reflect a sort of skeptical assumption or statement about the population parameter given the research question. So essentially, the null hypothesis is kind of the nothing interesting hypothesis. We'll denote this as H sub 0 or H sub naught or H null, depending on how you're used to seeing that subscript. The alternative hypothesis is then the competing alternative. If we can throw out the null hypothesis, then this is what we're left with. The alternative hypothesis is usually related to the research question in some way, and it's often just a direct restating of the research question. It might be what we had hoped to prove, what we had hoped to disprove, what we were looking for evidence for or against. The alternative hypothesis gets denoted H sub A. Now, there's a couple different forms for this. The alternative hypothesis can be what's referred to a one-sided alternative hypothesis. If we're looking at statements such as increase, decrease, those are changes in one direction. Whereas if we're looking at a two-sided hypothesis, we're just looking for an overall change. We don't really care if it's a decrease or an increase. So let's take a look at some hypotheses and determine whether or not they're one-sided or two-sided and state some corresponding hypotheses. So we've got 3 research questions here. I'll go through the answers for 1 and 2. We'll leave research question 3 for you to try at home. Let's look at research question number 1. Patients who take phentermine and topiramate lose weight at a different rate than control patients without these drugs. So we are looking at weight loss. Weight loss is a numerical value, so we'll be interested in a population mean, mu here. I'll let mu be the mean weight lost. We're interested in whether or not there is a difference. We care if they lose weight faster. We also care if they lose weight slower. So this is what we would call a two-sided alternative hypothesis. Our research hypotheses in statistical terms are going to look something like this. Our null hypothesis is an equality statement. We're assuming that the mean weight loss under the treatments is exactly the same as the mean weight lost under the control. For the alternative hypothesis, we're assuming that the mean weight lost under the treatments is not the same as the mean weight lost under the control. Let's look at the second research question. The second question says that artesunate is less effective than quinine at treating children with severe malaria. So here we're looking at malaria treatment. One indication of success might be a speedy or a fast recovery. So we'll let P be the proportion who recover from malaria. If artesunate is less effective, then fewer children with severe malaria will recover under that treatment than under quinine. So our null hypothesis, our equality assumption, is that artesunate is equal to quinine in terms of the recovery rate. Our research question, or the alternative hypothesis, is that artesunate has a lower or a less recovery rate. So that's step 1 of our test. Step 2 is to calculate the test statistic. The test statistic refers to a number that comes from our sample data that can be used to evaluate how far the data we've observed are from what we would expect if the null hypothesis is true. Now, this test statistic will change from situation to situation and from test to test. We know by now, because we've done some work with sample variation, that the data doesn't always reflect the population. But a lot of the time that's pretty close. So depending on what our random sample looks like, where that test statistic falls, we can start to say something for or against one of the hypotheses. A common form of a test statistic is this. We very often will take our sample statistic, whatever that is, subtract the expectation under the null hypothesis, so what would we expect our samples to look like if the null was true, and then divide by the standard error. This choice depends on some things. There's actually 2 criteria we'll use. Depends on the type of data we're analyzing, whether we have a single sample, multiple samples, numerical data, categorical data. It also depends on what assumptions we're willing to make about what our population looks like. So whatever technique we use to calculate this test statistic, we will then translate into a more consistent measure. So a measure of evidence, or a measure of the strength of evidence that is consistent from one type of hypothesis test to another, is something called a p-value. So what this p-value tells us is the probability of observing a sample statistic as or more extreme as the data we have collected, assuming the null hypothesis is true. In other words, what's the probability that we would get a sample even more unusual than the one we observed, assuming the null hypothesis is true? Now, this p-value is not the same as the probability that the null hypothesis is true. Think about that null hypothesis as either a fixed value. It's true or it isn't. We're not assigning probability to that. What we are saying is, okay, assume this null hypothesis is true. What's the probability then that we would get data like ours? Now, how we calculate this p-value changes, but how we interpret it does not, because at its core, this p-value is a probability. That means that no matter what test we're doing, the p-value will be on a constant scale from test to test. So we can assess that evidence in a similar way, no matter how we do things, which is really powerful. Here's how we will make a decision. So if this p-value is small, whatever small is defined to be, we will reject the null hypothesis. So remember, this p-value is calculated assuming that the null hypothesis is true. So it's based on an assumption. What's the more likely or the more reasonable explanation for a small p-value? Is it more reasonable that our sample data was just unusual, kind of weird? Or is it more reasonable that that assumption that we started out with probably wasn't correct, wasn't true? So if our p-value is small, we typically will go with explanation number 2. Our sample data isn't unusual. If we have a large enough sample, if we have a random sample, we can feel more confident in saying that our sample data isn't that weird. It's more plausible that our null hypothesis was just a wrong assumption. Now, let's say that the p-value is relatively large, and again, we'll leave this small or large discussion for a little bit later. But if that probability is big enough, we'll fail to reject our null hypothesis. Essentially, what that means is that the data isn't discredited by the null hypothesis. The data could plausibly have come from a population where the null hypothesis is true. Again, we're not implying that the null hypothesis is true, more that it's consistent. Our data specifically is consistent with what would happen if the null were true. How small is large? How small is small? How large is large? Ugh. It depends. We'll talk about that. You may have actually seen a hypothesis test before. So in, for example, BioLab, you likely collected some data, put it into Excel, looked for something called a p-value. More than likely, if you've done this before, or if you've seen this before, you've compared your p-value to something called 0.05, or a significance level of 0.05. Now, I'm here to tell you that significance level on its own is fairly arbitrary, and in fact, it's actually a pretty serious, rough source of contention in the sciences right now. Where do we set that p-value to? What should be that magical threshold for which we reject an alternative hypothesis? Throughout this course, I'm going to remind you that an arbitrary threshold is just that, arbitrary. We don't want to interpret this p-value alone. We want to take things like the quality of data, the size of the sample into account as well. The smaller this p-value gets, the stronger the evidence against the null hypothesis is, and that's really what we're going to try to look for here, is the strength of our evidence. So again, that significance level is a predetermined value that we'll compare the p-value to. We would like to, if we're using a binary cutoff, pre-decide what that is, just to avoid biasing our results. Essentially, what we mean when we have a small p-value is that we have strong enough evidence. There's enough there to really convince us that the null hypothesis is wrong, is false. If the p-value is greater than alpha, or greater than that significance level, what we say is a little bit different. We actually say that we fail to reject the null hypothesis. We don't have enough evidence to throw it out, but we also don't have concrete evidence to prove it either. The reason we can't prove the null hypothesis is because in order to do so, we would need to have data about the entire population, which we can't. We can either conclude that the null hypothesis is credible, we fail to reject it, or it's not credible, we reject it. Again, most disciplines will use alpha equal 0.05 by default and use this phrase statistically significant as sort of a magic seal of approval. We'll shy away from that phrase and just talk about how strong our evidence for or against some conclusion actually is. For us, here are the things we want to consider. How strong is the evidence from the p-value? How trustworthy is the sample? And then finally, what are the consequences of being wrong? Is it less important or less severe for us to be wrong in one way than it is in another? So the final step in a hypothesis test is to make a conclusion, and there are a few things that always will need to be included in that. Our decision is probably the most important thing, so whether or not we're rejecting or failing to reject the null hypothesis. I'd also like to see your rationale for this. So why are you making this decision? This refers to things like your test statistic, especially your p-value. It's usually sufficient to just put these in parentheses or state them outright. And then finally, we want to include an interpretation of the decision in context. Statistics shouldn't be done alone. It's the language of the sciences. So we need to be able to translate our conclusions back into the sciences. So what are the implications? How have we answered the research question? So let's take a look at some examples. A body mass index in adults of 25 or greater is considered overweight. Based on the data that we've seen previously from the NHANES sample, is there strong enough evidence to show that the population mean BMI is greater than 25? Well, here's our sample of data. 25 is right about here, right about in the middle of body mass index. Certainly there are a lot of people below 25. There are a lot of people above 25. So the data itself isn't as conclusive. We need to do some digging. We'll do some digging by using hypothesis tests. So let's go ahead and work through the steps. We'll let mu be the mean BMI. Our research question here is whether or not there's strong enough evidence to show that the population mean BMI is greater than 25%. So our null hypothesis, or our equality assumption, is that mu is equal to 25%. Our alternative hypothesis, this should be a greater than symbol here, so apologies for that, is that the mean body mass index is greater than 25. Our test statistic then usually follows a similar form. For this particular example, the type of test statistic that we'll use is actually called a t-statistic. We'll take our sample mean, we'll subtract a quantity called mu0. This is the value we would expect if the null hypothesis were true. And then we'll simply divide by the standard error. So plugging all of this in, we get a test statistic, or a t-statistic, of 2.7. So what this tells us is that our sample mean is about 2.7 standard errors from what we would expect if the null hypothesis were really true. That's pretty far away. That's pretty unusual. We'll then calculate the p-value and write a conclusion for the test. We'll talk a lot about what this looks like for different scenarios, so don't worry too much about the code right now. In the output, though, we want to look for something called p-value, and here it is. The probability of getting a sample mean like this, or one even higher, if the null hypothesis is true, is only 0.004. It's a very small probability. So based on our sample, we will reject our null hypothesis because this p-value is so small. There is strong evidence here to conclude that the population mean body mass index is greater than 25. Now remember, a p-value is a probability, so it's bounded between 0 and 1. 0 is as small as this p-value can get, so we're certainly approaching a very small p-value. Let's take a look at another example. So we're looking in this example at mercury concentration in fish. So we have data from a study of mercury levels of saltwater fish caught off the New Jersey coast. It found that a sample of 23 bluefin tuna had a mean mercury level of 0.54 parts per million and 0.15 parts per million. Why do we care? Well, mercury in the bloodstream can be dangerous. The general consensus here is that fish with mercury levels above 0.5 parts per million are too high to consume. Does this sample suggest that bluefin tuna off the coast of New Jersey is dangerous? Well, we'll start with our null and alternative hypothesis. Here is the summary statistics from our sample. We know that the fish are unsafe to consume if the mercury levels are above 0.5 parts per million, so that's going to be our criteria that we'll use. Mu is then the mean mercury level. Our null hypothesis is that the mean is exactly equal to 0.5, so that we're right at that cutoff. Our alternative, this should say HA here. What we're trying to show, or what the research question is really asking, is whether or not the mean is in fact greater than 0.5. We'll calculate our test statistic, and we'll do so just like we did in the previous example. We get a test statistic of 1.49. So this means that our sample mean is about 1.4 standard errors away from what we would expect if the null hypothesis is true. So it's certainly above what we would expect to get, but it's not that far above. Remember, about 2 standard deviations or 2 standard errors is when those red flags start to go up. So again, don't worry about the code for now. We'll look in the output for our p-value. It's right about here, 0.08. So there's about an 8 to 9% chance of getting a sample like this. Certainly a small probability, but is this the kind of probability that we would be shocked by? Probably not. So based on our sample, I would probably fail to reject at this point. There is maybe a little evidence, but certainly not strong enough to conclude that the population mean mercury level in bluefin tuna is greater than 0.5. Now, if we wanted to have stronger evidence, or if we wanted to improve our decisions, we might consider taking a larger sample, because we do only have 23 fish in this data set, relatively small. Now, let's talk about the types of errors where a hypothesis test can go wrong, because these certainly are not foolproof. Two outcomes of a hypothesis test will result in a correct decision. Two will result in an error. And let's talk about what these errors are. The first type of error that we could commit, statisticians are famously not imaginative when it comes to naming things. So our type 1 error is the first type of error that we could observe. A type 1 error will happen if we reject the null hypothesis when it is actually true. So our null hypothesis was a true statement, we chucked it anyway. Our type 2 error occurs if we fail to reject the null hypothesis when it's actually false. So our null hypothesis was wrong, but we didn't find enough evidence in the data to disprove it or discredit it. So let's take a look at an example. We have a patient who's been diagnosed with fibromyalgia, which is a long-term syndrome of body pain, and she's been prescribed antidepressants to help try to treat it. Being a skeptic, the patient doesn't initially think that these antidepressants will really help. However, after a couple months, she decides that, hey, these must be working, because she feels like her depression symptoms are getting better. So our type 1 error, what is that going to represent? First, we need to know our hypotheses. Our skeptical claim here is that the antidepressants aren't working. So our null hypothesis would be that the antidepressants are not helpful. A type 1 error would reject that. So this would be if our patient decides the antidepressants are working when they in fact really are not. Our type 2 error would be if the patient decides that the antidepressants are not working when the drugs actually are. Now, which is worse for our patient? I would make the argument that a type 2 error is worse here. If the patient decides that the antidepressants are not working, they'll probably stop taking them, which means that their fibromyalgia symptoms would begin to come back. The type 1 error we could think of as kind of the placebo effect. Our patient decides that the antidepressants aren't working. Medically speaking, they're not, but if the patient feels an improvement, then we've gotten somewhere. Now, unfortunately, we can never prevent these errors. There will always be errors in a test, but we can try to take some steps to control them. For example, the smaller we set that significance level alpha to be, the less likely it is that we'll make a type 1 error. And that's why the alpha rate is usually set so low, 0.05 or lower, because we really want to be certain that we're not making those types of mistakes. In order to minimize the probability of a type 2 error, we do this with a couple different techniques. The most common one is to choose a test with what's called high statistical power. The higher the power, the more likely it is that the test will lead to a correct decision. The probability that a random sample taken from a population will lead to a correct rejection if the null is truly false. So the higher the power is, the lower the probability of a type 2 error. The good news for us is that throughout the course, we will only focus on those types of statistical techniques that have already been shown to have high power. So for a given situation, we will just limit our attention to the most powerful tests. Let's take a look at one more example for this video. Balsamra is a drug prescribed for insomnia. We have a randomized placebo-controlled clinical trial that finds that patients assigned to take Balsamra for 3 months fell asleep 35 minutes faster on average than they did before the study. The study reports that this is a statistically significant improvement. Basically, their p-value was less than 0.05. Let's think about the practical implications of this. Would you consider falling asleep 35 minutes sooner, or an effect size of falling asleep 35 minutes sooner, important? Absolutely. If I fell asleep half an hour sooner than I did before, that is a major practical difference in the quality of one's sleep. So that is a practically important or practically significant or a clinically relevant result. Think about another situation. So patients assigned to take a placebo for 3 months fell asleep faster than they did originally, 27 minutes faster in fact. Also a significant difference. Here's the difference between taking Belsomra and taking a placebo. About 4 minutes faster with Belsomra versus the placebo. Is that 4-minute effect size important? Maybe, maybe not. Certainly falling asleep half an hour sooner is noticeable. 4 minutes sooner? That's a Taylor Swift song. Is that an improvement? Maybe it's not that noticeable. So we will stop here for this video. In the next few, we will start to dig more in depth into these different types of confidence intervals, hypothesis tests, and statistical models for a given scenario. So I will see you all then. Have a great day.